Hi there, and welcome to your lesson on series and parallel circuits. Specifically today we're going to take a look at Kirchhoff's rules. It comes from our man Gustav Kirchhoff, 1824 to 1887. He had a pretty good life, actually, old Gustav here. But lived a long time ago and did some really interesting early work on trying to understand if there was a mathematical relationship between currents and electric potential changes in a circuit. And if those mathematical relationships existed, how could we use those to engineer or construct circuits to get us to do what we want them to do? So that's our objective today, is to understand his two rules, one for current and one for electric potential changes. And we're going to apply them to a number of scenarios. So the first thing that we need to remember is what a series and parallel circuit is and how they differ. And so let's sketch one out real quick here. So let's say we've got a circuit that is coming out of a wall, 120 volts AC. So this is coming out of your wall. And let's draw this circuit so that it's representative of what we might see in our homes. So this is a fuse, symbol for a fuse. And then it's going to go to a switch. And the switch just happens to be open. And then we've got a light bulb connected to this circuit. And we got another light bulb connected. And then we've got a wall outlet. Those lines are supposed to be relative to each other, different sizes. And we got another outlet. And then this circuit can go all the way home. Okay, so this is a series circuit, and I'm sure you know that. The problem with the series circuit is that if one of these guys blows or functions to not let the electricity flow from one side along the pathway, then the whole thing turns off. The benefits is that using one switch, you can control the entire line. We're going to find out what some of the other advantages and disadvantages are when we start looking at Kirchhoff's rules. Though, to get us started with a parallel circuit, let's once again have our circuit coming out of the wall at AC 120. So we'll have this guy coming out, that guy coming out, and once again we'll have, because we're safety conscious, we want to have a fuse, which is one of my favorite symbols. And then we're going to have a junction where the electrons can choose a path to go to. We are going to have this one as an open switch, going to the light bulb, and going back to the wall. So that's one circuit. Another pathway, another circuit is going to look identical to the first. So another switch, going to another light bulb, and going back to the pathway. And then this guy is going to go to a wall outlet. And then it will run back to the wall. And then in this domestic one, we're going to have another wall outlet. A wall outlet, which is connected back to the wall. So in this way we have multiple paths going. You can have the lights off. You can have the lights off, but still have these wall outlets working. And that's the benefit of having things in parallel, is you can have a dynamic electrical environment, and that's pretty good. So that's just a little reminder of this is a parallel circuit. Now, the important thing about a parallel circuit, and this is where the new stuff really begins here, is these junctions. You can see that we have a choice. Electrons have a choice. They can flow this way, or they can flow this way. Now, in order to flow down, of course, we would have to close that switch to allow electrons to flow. That's super important, and that's important because that's one of Kirchhoff's first rule. His current rule has to do with that junction point, and Kirchhoff's current rule, short form is KCR, Kirchhoff's current rule states this: at any junction, that is, any place where there's a choice of pathways, and I use the word choice, that's an anthropomorphization of what an electron can do, but it's either going to go this way or that way. It can't go both, unless we're talking about some quantum stuff, which would be a different story altogether. At any junction point in a circuit, the total current going into the junction equals the total current out of the junction. There we go, Kirchhoff's current rule. Let's take a look at what exactly that means. So, if we have a current, change up my colors here, if we have a current I coming out of the wall, and we're interested in this junction point here that I will clean up a little bit for us. We're interested in what happens at this junction point in relation to the current. So let's call this IT for total. So IT is equal to the total current out of the junction. So let's say we have, we'll call this I going the first direction. This is the first pathway, and let's call this I2 coming out. So electrons can go that way or that way. So the total current coming into the junction has to equal the total current coming out. So this is equal to I1 plus I2. So if this was 3 amps, not 30 amps, if this was 3 amps coming into the junction, then the sum of this plus this must equal 3 amps. So 3.0 amps going in. That means the current in each of those two sections must equal 2. Now what is that? Let's take a look at what this means exactly, because going into the second junction, now we have, let's say I1 is 1 amp, just to give us something to play around with. That means, therefore, I2 must equal 2 amps. So now we have I2 going into the second junction, which means that this current plus this current must equal 2. So they're both going to contribute or sum to that 2. So really what it's saying is the sum of all the individual currents in each of the pathways is going to equal the amount of current going in to the pathway. And if we measure that current at this position, it should also equal 3 amps. That is Kirchhoff's current rule. Every choice, every junction there is, the current going in has to equal the total current going out in each of the arms. What about Kirchhoff's voltage rule? What's that all about? Kirchhoff's voltage rule is a little bit different, and it says this: in any complete path in an electric circuit, the sum of the voltages, or as we know it, the potential difference, the potential increases, rises, equals equals, that's not how you spell equals. Some days you just need more coffee. Rises equals the sum of the potential drops. Stated another way, this says that the voltage coming out of a system, let's say we have 9 volts, these batteries have 9 volts of energy to spend, the sum of all of the energy expenditures has to equal the amount of voltage put in. So this would be 4.5 volts if these were equal light bulbs, and 4.5 volts. So half of the money would be spent, half of the voltage, half of the energy would be spent equally in each of these two loads. So the rises, that indicates the input of energy. We're giving 9 joules per charge, 9 joules per charge of energy to spend, 9 volts. And it has to be spent all the way before the battery gets, the electrons get back to the battery. And if these light bulbs are equal, the sum of the drops, that is the positions where energy is used, has to equal the amount of energy put in. If we take a look at a little diagram here to indicate that, or sorry, if we were to draw that out in a bit of a mathematical way, we can say that the delta V total is equal to V1 plus V2, and those should be delta V's, where this guy is delta V1, the first drop or the first usage of energy, and this guy can be delta V2. All right, well there you go. Now what does this imply? Well, this allows you to analyze and calculate pretty complicated circuit diagrams and situations, not only for safety but for serviceability. That is, can the circuit service the purpose and the machines that it is meant to service? We can also take a look at resistance, because as we know through Ohm's law, there's a relationship between resistance, current, and voltage. So even though Kirchhoff's laws talk about the current and the voltage, we can also talk about Ohm's law, and we can simplify for you how Ohm's law uses resistance instead of voltage and current in order to take a look at how different circuits, how we sum up and explain the resistance in different circuits. Using KVR, the voltage rule, we see that delta V total is equal to delta V1 plus delta V2, and we'll just introduce a third one. So the sum of all the voltage drops has to equal the voltage that's given. All that means is all the volts need to be spent before an electron returns back to the battery. However, from Ohm's law, we know that delta V is equal to I times R. So we can rewrite these guys with IR. So we have I total times R total is equal to the current at position 1 and the resistance at position 1 plus the current at position 2 multiplied by the resistance at position 2 plus the current at position 3 multiplied by the resistance at position 3. We can also then apply KCR, which says that I total is equal to I1 and in a series circuit, the I at each of those positions are all going to be the same. If we take a look, the current rule at any junction point in a circuit, the total current in the junction equals the total current out of the junction. But if we're in a series circuit where there are no junctions, the I at any position around the circuit will always be the same. So, because I's are all the same in a series circuit, let's restrict our conversation here to a series circuit. The I's are all the same. They apply evenly to all terms, so we can cancel them out. So resistance in a series circuit is represented in this way. The total resistance is simply the sum of all the resistances of all loads or other kinds of things that may offer resistance, such as wire length. So the total resistance is simply the sum of the resistance in a series circuit. What about in parallel? How can we talk about resistance in parallel? Because we may, and of course if we're working on electrical circuits in homes or in microelectronics that use lots of parallel circuits, we need to be able to calculate the total resistance in a system in order to engineer a safe and functional system. So let's take a look at a parallel system now. We'll change up the color just to spice it up in here. Okay, so let's take a look at our two rules. Let's use KCR for parallel circuits. Says the total current going into a junction equals the total current going out. So we can say the current total is equal to, and in a parallel there's going to be different junctions. So the sum of all the currents equals the total current going in. Remember that what that means? It means the total current going in is the same as the current here, but this first junction, this first choice is two different currents that together add to the ingoing current. And if this is the ingoing current, then the two red currents here sum to this ingoing current. Okay, so we're doing okay. If we apply Ohm's law to that, which rearrange for current is this guy right here, we can rewrite that as in the voltage drop divided by the total resistance. The total voltage drop, or the total voltage spent in the circuit divided by the total resistance, is equal to the voltage drop over the first resistance plus the voltage drop over the second resistance plus the voltage drop over the third resistance. And according to the voltage rule, KVR, the potential differences are all equal in a parallel circuit. In any complete pathway, the electric circuit, the sum of all the potential rises equals the sum of all the potential drops. So for resistance then, if we can cancel these guys out, to sum the resistances in a parallel circuit, we have to, and this is the central understanding, we have to take the inverse of the resistances. We can't just sum the resistances in a parallel circuit. We have to sum the inverses, and an inverse really is just 1 over that. Okay, this is the very fundamental difference between series and parallel circuits. We can really understand what that means if we look at some examples. In a series circuit, as you add resistances, the total resistance increases. And using Ohm's law, you know that if you increase the resistance, you're going to decrease the current. So if you want to slow down the current in a series circuit, we just need to keep adding resistance, and that makes total sense. However, in a parallel circuit, if we increase the amount of resistance in a parallel circuit, let's take a look and see what happens. Quite the opposite, actually. So let's say we have let's find the total resistance of the following situation. Let's say we have a 5 ohm resistor in parallel with a 10 ohm resistor in parallel with a 30 ohm. So we have some pretty big resistances, 5, 10, and 30. Now if we added if this was series, of course the total would be 45 ohms. But this is parallel, where it's not the sum of the resistances, it's the sum of the inverses of the resistances. So let's go ahead and solve this. And first of all, we got to find some common factors here. When you add fractions, all the bottom numbers have to be the same. So how do you make 5 into 30? You have to multiply by 6. So 6 over 30 ohms. How do you make 10 the same as 30? You have to multiply it by 3. Whatever you do to the top, you have to do to the bottom. So 3 divided by 30 ohms plus 1 over 30 ohms. Add those all together. We have, I don't even know what that is, 10 over 30 ohms, which is equal to 1 over 3 ohms equals 1 over RT. But now we need to get these guys, we have to solve for RT, so let's multiply both sides by RT. So that's going to cancel with that one. And we have to multiply both sides by 3. So that 3 will cancel with that 3. And we have 3 times 1. So we have 3 ohms equals the total resistance. Notice how bizarre this is. The sum of all the resistances together equaled 45 ohms if it were in series, but in parallel the sum is 3 ohms. This can be some finicky math. Remember always to find a common denominator. And you got to change one number into that other number, and you can do that just by multiplying the bottom and top by the same. So we made 5 into 30 by multiplying that by 6, and because we multiplied the bottom by 6, we have to multiply the top by 6. Okay, let's take a look at a couple of examples with some actual readings on this model here. We have the series circuit on top, where there are no junctions, and then the parallel circuit on the bottom. And I've introduced resistors to you there, the squiggly line thing. You can see the different styles of diagram. There's a resistor there. There's a switch, you're familiar with that, and then light bulb. You're probably familiar with that as well. So let's take a look at the flow here of electrons in the series circuit. You can see they're pretty slow. Must have a lot of resistance. And you can see that each of these are 10 ohms, so the total resistance in the series circuit is 30 ohms. You just add them together. More than that, Kirchhoff's law says that the voltage drop across each of the loads must equal the voltage put in to the system. So we got 9 volts coming into the system. Let's take a look. We've got a 3 volt drop there. A 3 volt drop across the third resistor. So 3 plus 3, Kirchhoff's voltage law says that the sum of all the voltage drops equals this sum of the voltage increases, so it should equal 9, and there's the third 3, which equals 9. So that's Kirchhoff's voltage law. The current law says in any junction, the total current going in should equal the total current coming out of the junction. When there is no junction, you can see we have a current of 0.3 amps everywhere along the circuit. Okay, so that's for a series circuit. How about now for a parallel circuit? So for a parallel circuit, you can see that there's definitely a reduction in the flow from here to here. And let's use Kirchhoff's law to see if the total current going into a junction equals the total current coming out. So we've got total current 2.7. That means the 2 of the outgoing currents must equal 2.7. We have 0.9 and 1.8. So that is true. If this is 2.7, we know that this should be 2.7 down here. Here we have current going in at 1.8. That means the sum of this plus the sum of this must equal 2.7, and we see that 0.9 and 0.9. Sorry, 1.8. Why is the current higher in this section than it is in this section? Because this section does not have any resistance. Low resistance, higher current. High resistance, lower current. In a series section of the game. Okay, what is going to be the total resistance of this circuit now? We have 10, 10, and 10. The total is 30, but for parallel, we have to do the inverse. So it's 1 over 10 plus 1 over 10 plus 1 over 10 is 3 over 10. And that is going to be equal to about 3.3 total resistance. So the smaller total resistance from the sum of the 3 resistance, because we have to use the inverses. All right, well there you go. Let's just see what happens here if we remove this. We should expect an increase in the flow rate. Let's take this guy out here, and we'll connect these guys with a wire. So we're seeing an increase in the current there, 0.9, 0.9, 0.9. Let's get rid of this guy, and we should definitely see the increase where all the energy is spent in heat in short circuit. Okay, there you go. Okay, well those are Kirchhoff's two laws, the current law and the resistance law. Let's take a look at the big ideas that you definitely need to have command of. So let's start right at the top. You've got the resistance rule, which says that the total amount of energy given to electrons has to be spent completely amongst all the voltage using loads. Kirchhoff's current rule states that the total current going into the junction or split in electric circuit equals the total current out of the junction. We can find the total resistance in a series circuit by simply adding the resistances together. In a parallel circuit, we can find the total resistance by adding the inverse of the resistances together. And applying these equations for Ohm's law, KCR and KVR, and equivalent resistances, it can help us solve for unknowns or even engineer the conditions in a circuit that has to happen if we're to make a functional circuit. All right, so there you go. KCR, KVR, Kirchhoff's laws, finding resistance in parallel circuits. I hope this helped. We will talk to you soon.